Here's the honest version of this claim before anything else, because it changes how you should hear everything that follows. Leaving Mars and getting home isn't physically impossible. It's not a law of nature the way faster-than-light travel is. But for the first humans who actually land there, never coming back isn't science fiction pessimism either. It's the plain, unglamorous conclusion of real engineering studies, real NASA health data, and a real ongoing failure to solve the one problem that matters more than any other: manufacturing enough rocket fuel on Mars, using nothing but what's already there to lift a spacecraft back off the surface. Nobody has done that yet. Nobody currently has a fully worked out plan for how to do it at the scale required. That single unsolved core problem is the real reason so many serious engineers, not just internet skeptics, think the first Mars crew should honestly expect to stay. A conclusion that, as you'll see, even the person building the rocket has stopped trying to hide from the people who might one day fly on it. Start with the trip itself, because even getting to Mars operates on a schedule nobody controls. Earth and Mars don't orbit the Sun in sync. They line up for an efficient transfer only once roughly every 26 months. When the fuel-minimizing path known as a Hohmann transfer becomes available, a maneuver that takes advantage of the two planets' nearly circular orbits to minimize the fuel needed for the trip. Miss that window, and the next one doesn't arrive for another 2 full years. A delay with essentially no workaround short of an enormously more fuel-expensive trajectory that current mission architectures simply don't budget for. Even during the best alignment, the one-way trip takes somewhere between 6 and 9 months, exposing a crew the entire time to a spacecraft environment with no planetary magnetic field or thick atmosphere to block the two most dangerous forms of space radiation: solar particle events thrown off by the sun in unpredictable bursts, and galactic cosmic rays, high-energy particles blasted out by exploding stars and other extreme events elsewhere in the galaxy, arriving from every direction at once and largely unstoppable by anything short of very thick, very heavy shielding. NASA's own Curiosity rover carried a radiation assessment detector on its own trip to Mars specifically to measure this, and its data, once converted into a human dose equivalent, worked out to roughly the radiation exposure of getting 24 full-body CT scans spread across a single 180-day transit, or somewhere around 15 times the annual exposure limit currently set for nuclear power plant workers on Earth. That's the price of admission just to arrive safely at all. It hasn't touched the surface stay yet, where Mars's thin atmosphere, less than 1% the density of Earth's, and stripped of any global magnetic field billions of years ago, offers only a fraction of the shielding Earth naturally provides, or the trip home, which would expose a crew to that same 6 to 9 month radiation dose all over again. NASA has spent years formally cataloging exactly what that radiation, combined with everything else about deep space, does to the human body through its Human Research Program, and the findings are sobering enough that the agency ranks them among its highest priority so-called red risks, the category reserved for hazards judged both likely to occur and severe enough to threaten a mission or a crew member's long-term health and quality of life for the rest of their years, not just during the mission itself. Space radiation is linked to elevated cancer risk, cardiovascular disease, and measurable cognitive decline, effects that in some cases may not fully manifest until years after a crew member returns, assuming they return at all. Microgravity and the pressure shifts of long-duration spaceflight cause something NASA calls spaceflight-associated neuroocular syndrome, a condition first identified in International Space Station astronauts, where fluid shifts in the skull can permanently distort an astronaut's eyesight, flattening the back of the eyeball and swelling the optic nerve in ways that don't always fully reverse once someone returns to Earth's gravity. Add to that the psychological toll of genuine isolation and confinement, months inside a metal can with the same handful of people, no ability to leave, no real-time conversation with anyone back home due to communication delays that stretch up to 20 minutes each way at Mars's farthest distance from Earth, meaning even a simple question and answer exchange could take the better part of an hour. And NASA's own researchers list behavioral health and performance decline as a top-tier risk in its own right. None of this is speculative. It's documented, peer-reviewed, and actively studied specifically because NASA is trying to solve it before committing astronauts to the trip. Long before anyone builds a real Mars habitat, researchers have already tried to simulate what years of isolation like that actually do to a human crew. And the results are its own quiet warning sign worth taking seriously rather than dismissing as a mere laboratory curiosity. The Mars 500 project, run by Russia's Institute of Biomedical Problems with support from the European Space Agency, sealed 6 volunteers inside a windowless mock spacecraft outside Moscow for 520 days between 2010 and 2011, deliberately matching the full round-trip duration a real Mars mission would require down to the day, complete with simulated communication delays that stretched up to 20 minutes each way as the mock mission traveled farther from Earth, forcing crew members to adjust to conversations that could no longer happen in real time. Crew members experienced genuine psychological strain over the course of the isolation, including disrupted sleep cycles, reduced physical activity, and measurable shifts in mood and motivation among at least some participants over the course of the year and a half they spent sealed away from the outside world. Exactly the kind of behavioral health decline NASA now formally tracks as one of its top priority risks for real deep space missions. A separate ongoing series of analog missions on the slopes of Hawaii's Mauna Loa volcano, known as HICs, and run with backing from NASA, has put multiple crews through 4, 8, and 12-month stretches of simulated Mars isolation inside a small geodesic dome perched at high altitude on bare volcanic rock chosen specifically because it visually resembles the Martian surface, studying everything from crew conflict and cohesion to how quickly food cravings and sensory deprivation start affecting group dynamics when nobody can simply step outside for fresh air without first suiting up in a mock spacesuit and going through a simulated airlock procedure. None of these simulations can fully replicate the psychological weight of knowing you're genuinely millions of miles from home with no rescue option, and no way to simply walk out the door if things go wrong, a distinction analog researchers themselves are always careful to flag when presenting their own results to the wider public. But they've already surfaced real, recurring problems, communication breakdowns, irritability, and motivation loss among them that any real Mars mission planner now has to actively design around, rather than discover for the first time with an actual crew already committed to the trip and no way to turn back partway through. Food is its own understated piece of this puzzle, and it's worth taking seriously rather than treating as a minor logistical footnote easily solved with enough freeze-dried packaging. A round-trip Mars mission, factoring in transit time both ways plus a realistic surface stay time to the next return window, could stretch well beyond 2 full years, which means every calorie a crew eats either has to survive that entire span in storage without meaningfully degrading in nutritional value or palatability, or has to be grown on the Martian surface itself in roughly 1/3 of Earth's gravity, under artificial lighting powered by whatever surface energy system the mission has available, using soil that would first need to be treated to remove the toxic perchlorate compounds naturally present across much of the Martian surface at concentrations high enough to be harmful if left unaddressed. NASA's own nutritional research has found that many vitamins in pre-packaged spaceflight food degrade meaningfully over periods far shorter than a full Mars mission's duration, which is part of why the agency lists inadequate food and nutrition among its own red-tier risks for long-duration spaceflight, right alongside radiation and behavioral health, rather than treating it as a solved logistics problem. But even if every one of those problems got solved tomorrow, radiation shielding perfected, artificial gravity or effective countermeasures deployed, food and psychological support fully worked out, there would still be nothing built on Mars capable of getting a crew home. And that's the part of this story that isn't about human biology at all. It's about chemistry, and it's the part almost nobody solves in these conversations, because it's genuinely the hardest engineering problem in the entire enterprise. A spacecraft can carry enough fuel to get to Mars. It cannot practically carry enough fuel to get to Mars and back, because rocket fuel is heavy, and every extra pound of return trip propellant has to be launched from Earth's surface too, fighting Earth's own gravity on the way up before it ever gets the chance to do anything on Mars. The only realistic solution anyone has proposed is called in-situ resource utilization. Building a chemical plant on the Martian surface that pulls carbon dioxide from the thin Martian atmosphere and, combined with water ice mined from the ground, manufactures methane and liquid oxygen, essentially brewing rocket fuel from local ingredients rather than hauling it 140 million miles from home. It's a genuinely elegant idea on paper, and it's the specific plan SpaceX has built its entire Starship to Mars architecture around, a plan Musk has publicly described in broad strokes for close to a decade, without the underlying chemistry ever changing, only the scale of the challenge becoming clearer. The basic chemistry involved, sometimes called the Sabatier process, after the French chemist who first demonstrated the reaction in the early 20th century, combines hydrogen with carbon dioxide, pulled from the Martian atmosphere to produce methane and water, and that water can then be split by electrolysis into hydrogen, which gets fed back into the loop, and oxygen, which becomes both breathable air and the oxidizer needed to burn the methane as rocket fuel. It's chemistry that works perfectly well in a laboratory on Earth. And NASA has even flown a small demonstration version of it to Mars already, a toaster-sized instrument called MOXIE that flew aboard the Perseverance rover and successfully produced small amounts of oxygen directly from the Martian atmosphere across more than a dozen individual test runs between 2021 and 2023, proving the underlying chemistry is sound under real Martian atmospheric conditions, rather than just in a simulated chamber back on Earth. The problem isn't whether the reaction works. It's turning a toaster-sized proof of concept that produced roughly a dozen grams of oxygen per hour into an industrial-scale chemical plant capable of producing thousands of tons of propellant, a jump in scale that dwarfs anything demonstrated so far by a factor in the thousands, requiring power, plumbing, and reliability, entirely unlike anything a small rover-mounted instrument was ever asked to deliver. The problem is the scale nobody outside the technical literature seems to appreciate. Independent researchers, publishing in the peer-reviewed journal New Space in 2022 as part of a broader mission architecture study, calculated that returning a Starship-class vehicle from Mars would require manufacturing roughly 2,400 metric tons of propellant directly on the Martian surface, and that doing so would need a power system on the order of 4 megawatts, dedicated purely to running that chemical plant. A power output roughly 100 times larger than any surface power system NASA currently has in active development for Mars. A separate independent study published in Nature's Scientific Reports journal in 2024 modeled SpaceX's publicly stated Starship mission architecture directly, using detailed mass budgets built from publicly available information about crew consumables, payload, and propellant requirements, and reached a blunter conclusion still. Based on the vehicle's own mass budget, current plans simply do not produce a viable return flight opportunity at all, because the spacecraft, fully loaded with the propellant a return trip would require, becomes too heavy for the mission profile to close. The same researchers flagged that critical supporting technology, especially that Mars surface power supply, likely can't be developed in time, even by the end of this decade at current funding and development rates, and recommended bringing in far more international collaboration just to have any realistic chance of closing the gap between the current state of the technology and what a genuine return mission would actually require. Elon Musk himself, to his considerable credit, has never actually hidden any of this behind marketing language, and it's worth hearing the plan's own architect describe the risk in his own words, rather than assuming the danger is only something critics have invented. Speaking at the International Astronautical Congress back in 2016, Musk told prospective early Mars travelers, the honest pitch was essentially, "Are you prepared to die?" warning that the risk of fatality on the first journeys would be high with, in his own words, no way around it whatsoever. He's returned to that same blunt framing repeatedly in the years since, telling interviewer Peter Diamandis in a 2021 conversation that a meaningful number of early travelers would likely not survive, describing the journey as arduous and dangerous with no guarantee of coming back alive, while still calling it a glorious adventure in the same breath, and comparing the recruitment pitch directly to explorer Ernest Shackleton's famously grim newspaper advertisement seeking volunteers for a hazardous journey to Antarctica over a century earlier. As recently as December 2025 on the Katie Miller podcast, Musk pushed back explicitly against the idea that Mars would function as a comfortable escape hatch for the wealthy, describing early settlements on both Mars and the Moon as cramped, uncomfortable, and carrying a meaningfully higher risk of death than simply staying on Earth, invoking the early English colony at Jamestown, where a majority of the original settlers died within their first years, as the more honest historical comparison than anything resembling a vacation. That's not incidental color, it's the person actually building the rocket, telling prospective crew members, on the record, across nearly a decade of consistent messaging, that survival itself, before any conversation about a return trip even starts, is not guaranteed. That's not a criticism from a skeptic looking to score points. It's the same conclusion the mission's own architecture keeps running into in practice, which is exactly what's been playing out in public over the past year, in enough documented detail that you can trace the entire retreat announcement by announcement. Elon Musk spent much of 2025 promising that SpaceX would launch its first uncrewed starships toward Mars by the end of 2026, timed to the next available transfer window, with human landings potentially following as soon as 2029, though Musk himself repeatedly hedged that 2031 was more realistic, and gave the 2026 uncrewed attempt only roughly a 50-50 chance of actually happening on schedule. As late as August 2025, Musk was still describing plans for 5 Mars-ready starships, and the Italian Space Agency had reportedly signed a contract to fly its own experiments aboard the mission. Multiple 2025 Starship test flights ended in explosions instead, including a mid-flight breakup in March that scattered debris over Florida and the Caribbean and triggered a full FAA safety review, one of several incidents that repeatedly grounded the vehicle for extended stretches while investigators traced the failures back to their root causes. By May 2025, the Wall Street Journal reported that SpaceX had told investors it would prioritize the Moon first and delay any Mars landing attempt to a later, unspecified date, a direct acknowledgement that lunar commitments tied to NASA's Artemis program were consuming resources and attention the Mars effort would have needed. Throughout the back half of 2025, Starship's next major test flight itself kept slipping too, bumped from an initially planned March liftoff to April, then to May, then further still, as SpaceX worked through preparations for a larger, more advanced vehicle variant. Then, in a podcast recorded in late December 2025 and published in January 2026, Musk himself described the 2026 Mars mission as a distraction from other priorities, which functionally confirmed what outside observers had already suspected. The uncrewed 2026 Mars mission, the one meant to test exactly the kind of hardware a future return trip would depend on, has been quietly shelved. This isn't a story about any one person's promises falling short. It's a direct, real-time illustration of exactly how hard the propellant and power problem actually is. The company with by far the most capital, the most public ambition, and the most test flights under its belt in this specific area keeps running into the same wall. The peer-reviewed engineering literature already predicted it would, year after year, announcement after announcement, slipping in exactly the direction the mass and power calculations said it eventually would have to. It's worth putting that risk tolerance in historical context, because it's easy to assume modern spaceflight has always demanded near-certain safety when the record actually tells a different story. NASA's own Apollo-era astronauts reportedly estimated their own odds of a fatal outcome on the first moon landing at somewhere around 1 in 10, a level of accepted risk that would be considered wildly unacceptable by the safety standards applied to human spaceflight today, decades of hard-won engineering experience later. 3 Apollo astronauts died in a launch pad fire during a ground test in 1967, and 14 more were killed across the Space Shuttle program's Challenger and Columbia disasters, tragedies that each triggered years-long program halts and fundamental safety overhauls precisely because the agency's tolerance for risk had shifted so far from where it stood during Apollo. Whether a modern Mars program, operated by a private company answering primarily to investors, and a charismatic founder rather than to the same layers of congressional and public oversight NASA operates under, would actually hold itself to Apollo-era risk levels, shuttle-era risk levels, or something else entirely, is itself an open and largely untested question. One that hasn't yet been forced into the open by an actual fatal incident, the way it eventually was for NASA twice over the course of its own history. It's worth being fair about what NASA's own plans actually look like, because they're built differently and more conservatively than SpaceX's, and understanding that difference is itself part of the honest answer to why the two organizations keep landing on such different timelines for the same underlying goal. NASA's stated Mars architecture, still years away from a committed timeline of its own, generally assumes pre-positioning return propellant and habitat elements on the Martian surface years in advance of any crew launching at all, verified and fueled before a single astronaut leaves Earth, precisely because the agency has internalized the lesson that you cannot simply build the return capability after people have already arrived and are depending on it working on the first try. This mirrors the same staged, prove-it-first philosophy NASA has followed with its lunar Artemis program, where uncrewed test flights and robotic landers are meant to validate hardware well before any astronaut relies on it. That's a far safer approach than betting a crew's survival on manufacturing a return vehicle's worth of fuel for the first time, while they're already standing on the surface waiting for it to work, with no backup plan if the chemical plant underperforms or fails outright. But it's also a far slower, far more expensive one, requiring multiple successful uncrewed missions to fully validate the return infrastructure before anyone commits a crew to using it, which is a large part of why NASA's own crewed Mars ambitions remain pushed out well beyond the current decade, tied loosely to broader Artemis program lunar milestones that themselves keep slipping, and dependent on political and budgetary support across multiple presidential administrations and congressional funding cycles that has historically proven difficult to sustain for any single space program over the 15 to 20-year span a genuine Mars return architecture would likely require. This is precisely the gap that turned Never Coming Back. From science fiction shorthand into an actual, real funded proposal, a real organization tried to build an entire business around. Mars One, a Netherlands-based venture founded in 2011, pitched exactly this trade-off explicitly. Skip the return trip entirely, and the mission gets dramatically simpler, cheaper, and more achievable, because you no longer need to solve in-situ propellant production, a second launch vehicle capable of surviving years on the Martian surface, or a return trajectory at all. Company co-founder Bas Lansdorp framed the plan around exactly the same radiation and engineering realities discussed here, arguing publicly and repeatedly in interviews and on the company's own website that a one-way trip sidestepped the single hardest unsolved problem in the entire field rather than pretending it away or promising a solution the industry hadn't yet demonstrated. More than 200,000 people applied to be among the first colonists, eventually narrowed down to a short list of just 100 candidates who would have been sequestered together for years of joint training before launch, drawn to a project that promised to fund itself partly through a reality television series documenting the selection and training process, turning humanity's first Mars settlers into a global media spectacle rather than a purely scientific undertaking. The plan was, from the outside, seductive precisely because it sidestepped the hardest engineering problem in the entire field by simply declaring it out of scope. It didn't work. Independent experts spent years pointing out that even without a return trip, Mars One's proposed budget, life support systems, radiation shielding, and psychological support for astronauts who would never again see Earth were nowhere close to adequate for keeping people alive for the rest of their natural lives on another planet, with critics repeatedly flagging the group's roughly $6 billion funding target and its underdeveloped technical roadmap as fundamentally incompatible with what the mission actually required. The organization missed its original 2023 landing target, pushed the date back repeatedly toward 2031, brought in a Swiss financial firm to try to save its for-profit arm and secure fresh investment, and ultimately collapsed into bankruptcy in February 2019, dissolved after a Swiss court affirmed its insolvency, having listed debts of roughly €1 million without ever launching a single test mission toward Mars or sending a single candidate into any form of real space training. Mars One's failure doesn't prove one way Mars settlement is impossible in every case. But it's a real, thoroughly documented case study in exactly how difficult, even the simplified, no-return version of this problem turns out to be once actual engineers and actual budgets get involved, rather than a marketing pitch, a reality show concept, and a wish list. So where does that leave the honest answer to why anyone who eventually does go to Mars might genuinely never come home? Not because of any single dramatic failure, and not because return is physically forbidden by the laws of the universe. It's the accumulation of several separate, well-documented problems stacking on top of each other, each one individually survivable in isolation, but compounding into something far more serious once a real mission has to solve all of them simultaneously, on a fixed budget, under real deadline pressure. The orbital mechanics only offer a return window once every 26 months. Meaning any delay, mechanical, medical, or logistical, doesn't just cost days, it can cost years, stranding a crew on the surface for an entire additional transfer cycle if anything goes wrong at the wrong moment. The radiation exposure of 2 additional transits, in and out, on top of however long a crew spends on a radiation-exposed Martian surface with a thin atmosphere and no global magnetic field, pushes cumulative dose into territory NASA's own health researchers rank among the most serious risks in all of human spaceflight. Risks that compound with every additional day spent away from Earth's protective magnetic field and atmosphere. The psychological weight documented in every analog isolation study run so far, Mars 500, HICs, and the smaller missions that preceded them, suggests the mental toll of true isolation is its own genuine hazard, not a footnote to the physical risks. And underneath all of that sits the propellant problem, still unsolved at the scale required, that every independent engineering analysis, not just one skeptical outlet, but peer-reviewed studies in Nature's own scientific reports and in New Space, keeps confirming is currently beyond what any announced mission architecture, including the one built by the best-funded private space company in the world, has actually demonstrated it can pull off. Add the genuine chance that political will, funding, or a company's own priorities shift mid-program, exactly as SpaceX's own 2026 mission just did, sliding from 5 ships and an Italian space agency payload contract down to Musk's own December admission that the whole attempt was a distraction, and every crew that lands on Mars before that fuel production problem is fully solved and independently verified is, functionally, making a one-way trip whether the mission plan says so on paper or not. That's a very different claim than saying it's impossible in principle, and the difference matters enormously for how you should actually think about this. Return from Mars is an engineering problem, not a law of physics, which means it's solvable in theory, given enough time, enough investment, and enough successful and glamorous test missions proving out surface power systems and propellant plants long before any human commits to relying on them. The same slow, staged, prove-it-first approach NASA has built its own program around, rather than SpaceX's faster, more aggressive one. The honest headline isn't that nobody will ever come back from Mars. It's that the first people who go almost certainly will be going before that return capability has been fully proven, accepting a level of risk closer to the explorers who set out across oceans with no guarantee of a return voyage than to the fully round-trip missions NASA has flown to the moon since Apollo. Whether that's framed as historic bravery or reckless promotion probably depends on who's doing the framing and how much they're personally on the hook if the fuel plant doesn't work, whether that's an astronaut standing on the launch pad or an executive whose company's reputation rides on the outcome. But the underlying physics and engineering, unlike most of what fuels a headline like this one, are entirely real, extensively documented across multiple independent peer-reviewed studies, and worth understanding on their own terms. Propellant chemistry, orbital windows, radiation dissymmetry, and all, rather than through the lens of a single dramatic sentence designed mainly to be clicked on rather than actually explained.